Hello everyone, I'm Bingbing Zhao, a PhD student from Georgia Tech. Today I'm going to introduce our work, a larger-scale empirical analysis of the vulnerabilities introduced by third-party components in IoT firmware. This is a joint work with students and professors at Georgia University, University of Virginia, and the Chinese Academy of Science. Nowadays, IoT devices have become popular and offer great convenience to our daily lives. However, IoT devices have become ideal targets of attackers, and many real-world attacks have been launched against IoT devices. Firmware currently widely adopts third-party components. However, the wide usage of third-party components will bring many new attacks to IoT firmware because many third-party components have known vulnerabilities. Besides, vendors may reuse the same third-party components in different firmware, which accelerates the spread of potential vulnerabilities. Therefore, it is important to recognize the vulnerable third-party components used in firmware. Many previous works have been proposed to evaluate the security of IoT devices, but they have several limitations. First, they lack the analysis of endless vulnerabilities introduced by third-party components. Second, they lack the consideration of non-Linux-based firmware. Finally, their scalability is a challenge when given a large-scale firmware test. So considering the critical situation, the question is how to build a scalable and automatic tool to identify the vulnerable third-party components used in IoT firmware. To answer the question, we need to first address three main challenges. First, there is no public firmware dataset for research, and many vendors prohibit the public from downloading firmware. Second, it is difficult to extract the different kinds of firmware and hard to deal with the monolithic firmware. Third, it is hard to distinguish the same third-party components at version level, and there is no third-party component database that indicates the possible third-party components used in firmware. To solve the above challenges, we propose Firmsec, a scalable and automatic framework to analyze the third-party components used in firmware and identify the corresponding vulnerabilities. And here is a brief overview of Firmsec. It has three components. They are firmware collection, firmware preprocessing, and firmware analysis. For firmware collection, we first collect public firmware from three sources: official website, FTP site, and community. Second, we collect private firmware from T-Smart. T-Smart is a world-leading company on smart homes. For firmware preprocessing, we first filter the obvious non-firmware files. Next, we adopt a tool to get rid of other non-firmware files. Then we identify the necessary information of firmware. For example, operating systems. Then we first extract the information from the metadata files of firmware. Next, we adopt Binwork to scan all firmware to obtain the operating systems, architectures, and file systems. Next, we extract the objects in firmware. We mainly use Binwork to extract the firmware and equip it with three plugins. Next, we disassemble the firmware. Many IoT firmware are monolithic firmware. They may use uncommon processors and miss some necessary information. So we need to recover this information. We first analyze the processors used in monolithic firmware to recover the missing information. For example, the RAM start address. Next, we customize 7 plugins for IDA to disassemble 7 kinds of processors. Next, we create a third-party component database that contains the possible TPCs used in firmware and the detailed vulnerability information for each TPC version. To begin with, we first collect the possible TPCs used in IoT firmware from 4 sources. Next, we query 3 databases to obtain the CVEs of each TPC. During the analysis, we find the syntactical features and control flow graph features are hardly changed between the source files and the binaries. So we decided to use these 2 kinds of features to identify TPCs in firmware. And here is an overview of our method. We first extract the above 2 features from TPCs and firmware. Second, we use the edit distance and the ratio-based matching to calculate the similarity of syntactical features. Finally, we use customized Gemini to compare the CFG features. Gemini is a system designed for recognizing the similar code between different binaries by comparing the CFG features. First, we extract the two features from TPCs. We first build a parser to extract the syntactical features from C source files of third-party components. Second, we extract the attributed control flow graphs from each version of TPCs. ACFG is defined by Gemini. Each vertex in ACFG is a basic block labeled with a set of attributes. And except for the block level attributes used by Gemini, we also adopt 3 function level features. Second, we extract the 2 features from firmware. We first equip IDA with a large number of signature files to identify the function names in disassembled files. Second, we customize extraction tool to get the ACFGs from the firmware. Next, we conduct syntactical feature matching. The first step is to calculate the edit distance between the syntactical features from TPCs and the firmware. If the edit distance exceeds the given threshold, we regard the features are matched. Next, we calculate the number of unmatched features. We calculate the ratio of matched features to all features extracted from the TPC. If the ratio exceeds the given threshold beta, we regard the TPC is matched. Next, we conduct CFG feature matching. The original Gemini cannot directly apply to TPC detection because it uses a single ACFG to detect specific vulnerabilities. However, given each TPC has many ACFGs, the similarity of a single ACFG cannot determine the similarity between the TPC and the firmware. Therefore, we first implement the customized Gemini. We give a high weight to the complex CFGs. Next, we normalize and aggregate the similarity of each ACFG based on the weight of the corresponding CFG. If the final similarity exceeds the given threshold, we regard the TPC is matched. Finally, we conduct vulnerability identification by 3 steps. First, we combine the results of syntactical feature matching and the CFG feature matching as the final results. Second, we automatically query the TPC database with the TPCs and the corresponding versions and record the returned vulnerability information. And based on the information, we generate a report for the tested firmware, and it has the potential risks and provides a series of suggestions for fixing the vulnerabilities. Next, we design several experiments to evaluate firmsec. We first give an overview of our dataset. Our dataset has 34,000 valid firmware images, and including 11,000 public firmware images and 23,000 private firmware images. And it involves 13 vendors and 35 kinds of different IoT devices. We first evaluate the model accuracy of firmsec. We train the customized Gemini on a ground truth dataset and see if the model when it achieves the best AUC. Finally, our AUC is 0.953, while the original Gemini is only 0.912. Next, we need to select the threshold for our system. We use the true positive rate at version level as the metric to select the appropriate thresholds. Then we select the thresholds when the true positive rate reaches the highest. Firmsec achieves the highest true positive rate when alpha equals to 0.74, beta equals to 0.52, gamma equals to 0.64. Finally, we compare our overall performance of firmsec with 3 works. We first create a ground truth dataset, and firmsec has a better performance than previous works, both at TPC level and version level. Firmsec achieves over 90% precision and recall at TPC level and version level. After evaluation, we perform firmsec on our dataset. We successfully unpack and disassemble 96% firmware images and we find 584 different third-party components used in 34,000 firmware images. According to the result, we have some findings. First, the routers from OpenWRT contain the most TPCs because it's reasonable because OpenWRT is an open source project for embedded systems. Second, smart homes from T-Smart use few third-party components. We also find most of the smart homes are using the monolithic firmware. We also find the same kind of firmware from different vendors use similar third-party components, and different kinds of firmware have commonalities in using third-party components. We then search the corresponding vulnerabilities in our database. We find a great number of potential vulnerabilities introduced by 429 CVEs, and 88% of the CVEs are caused by 10 CWE software weaknesses. And according to the result, we also have some findings. First, we find that most of the vulnerabilities are concentrated on a few third-party components, and 386 CVEs are from 10 TPCs, accounting for 90% of all the CVEs we detected. We also conduct further analysis to explore 4 research questions. First, we want to know how vulnerable are firmware images of different kinds and from different vendors. We first find the router is more vulnerable to attacks. Smart homes have very few vulnerabilities in each firmware image. Xiaomi has the most vulnerabilities, which causes Xiaomi more vulnerable to attacks. We surprisingly find 2 vulnerabilities have affected 604 firmware images, and 380 firmware images are vulnerable to the Heartbleed, and 224 firmware images from 4 vendors are vulnerable to the Ghost. Second, we analyze the geographical distribution of devices using vulnerable firmware. We use shorthand to get the distribution of vulnerable devices. We list the top 10 regions with the most vulnerable devices, and we find 6 regions located in Asia, and South Korea has the most vulnerable IoT devices. United States and Canada both have many vulnerable IoT devices, while Europe has relatively few vulnerable IoT devices. Next, we analyze the problem of delay times of third-party components. We want to know whether the firmware is still using the outdated third-party components. The results are surprising. We find the average delay time of TPCs for our firmware is about 2,000 days. It means the firmware images are using the third-party components that were released 5 years ago when the firmware is distributed. Finally, we analyze the license violation problem in IoT firmware. It's a very critical problem because it will introduce legal issues. We mainly study the GPL and AGPL license. We find 2,478 commercial firmware images that have potentially violated the GPL and AGPL licensing terms. And we also find 4 vendors have open source the source code of some licensed firmware, but we still cannot find the source code of all firmware images, which should be open source. And our analysis may raise serious ethical issues. Therefore, we pay special attention to legal and ethical issues. First, our firmware images are collected and treated legally, and we have reported all the vulnerabilities to vendors. Finally, we will open source the dataset with a legal and ethical issues-free plan. For the future work, we will collect more firmware images to extend the dataset, and we'll continue to enrich the TPC database. We will also adopt new techniques like fuzzing to conduct a more in-depth analysis. In conclusion, we propose Firm6, the first scalable and automatic framework for analyzing the third-party components using firmware and identifying the corresponding vulnerabilities. We have built so far the largest firmware dataset and conducted the first large-scale analysis of the vulnerable TPC problem in firmware. We also conduct further analysis from 4 different perspectives and uncover many problems. Besides, we have open sourced the dataset. Thanks for listening. Any questions?